welcome back to the lab. If you haven't already, go ahead and hit that subscribe button down below to make sure that you stay up to date with all the making, engineering, DIY, and topics like this that we cover in the lab. Today we're kicking off a new video series, and it starts with this. Now if you are from my generation, this sound means awesome. Alright, so what this series is going to be covering is retro console security, how it was designed, and eventually how it was bypassed, and then a separate video for each console with how to bypass it in 2020. And we're starting off with the genre of the PlayStation 1. Now, many of you know that this wasn't the first console to have piracy be an issue, or to have homebrew available to it despite the manufacturer's best efforts. However, this one was the first one that made it easy. And ever since then, it's been a cat and mouse game between the hardware security reverse engineers and the people who design this hardware. And that's what we're going to be looking at. We're going to take a look at how all of this was defeated, and we're going to move through with each individual console. We're going to do the PlayStation 1, we're going to do the PlayStation 2, we're going to do the original Xbox, we're going to do the Nintendo Wii, we're going to do the Xbox 360, and we're going to do the PS3. Oh, and the PSP, one of my favorite handheld, by the way. I'm generally an Xbox gamer, but the PSP is my favorite handheld since Xbox doesn't have one yet. Alright, so what do we know about the PlayStation original, PlayStation 1? It was born in controversy, is the first and foremost interesting part of the console itself. It was originally designed to be an add-on for a Nintendo console, but Nintendo decided at the last minute to basically screw Sony over, and they left them with an almost completed console. So, Sony, not really wanting to get into the video game market and into this massively competitive field that's already saturated, approached Sega to see if Sega might want to use the technology with one of their consoles. Just like Nintendo, Sega passed. So, Sony is sitting here. They have a mostly finished console that's CD-based, and nobody who wants to partner with them, so they decided to go into the video game market themselves. Nintendo's mistake and Sega's mistake cost them dearly. Nintendo is now relegated to just your casual gamer, and Sega doesn't make hardware anymore. Not saying this is directly because they didn't pick up the add-on from Sony, but it's because they didn't pick up the add-on from Sony. And that brought about a competition level that neither of these groups were ready to deal with. So, first off, this console does have security. And many people, including others who have made videos about this, have no idea what that security is. Okay, so the first thing that comes up when you talk about the security of the PS1 is this guy. If you're looking at through this camera, your standard PlayStation 1 game has a black bottom. Actually, it's violet, but the way the light works, it looks black. A lot of people will tell you that the black bottom of the disc has something to do with the security of the console. It does not. The lasers in these consoles can't see color. So, yeah, it has no idea whether it's a green bottom disc like this backup copy of Siphon Filter 3, which I just showed you I have a license for. I don't do the whole piracy thing. It can't tell the difference in the color, but what they did was actually fairly ingenious for the time. A lot of people will tell you that the console security is a joke, but okay, that's by today's standards. Given that this was, pre every console's connected to the internet, pre the ability to launch updates whenever you want to change something with the console, they actually had to do a hardware revision every time they wanted to change the security. And well, obviously that is costly and that takes time. So that was an advantage to the people looking to circumvent the security in here. One of the big pieces of how security was handled in the PlayStation 1 is based off of the region code. If you remember this boot screen, you will see the text at the bottom of the screen that says licensed by Sony Computer Entertainment of America, SCEA. It might surprise you to know that in this actual device, in all the firmware and all the programming that is in this device, that string does not exist. That string comes from the disc. Now, why does this happen? To be honest, it was kind of a failed idea of Sony to first stop unauthorized games from being able to be produced by third parties. They figured that because this actually is part of the region authentication for the console, anybody who wanted to produce games would have to put that string in, and then they'd be able to sue for trademark infringement since the string is trademarked. Nintendo thought the same thing, and a court case proved them wrong. So I don't think it would have worked for Sony. I'm not aware of any court cases that went on. For Nintendo, it was against Atari, who was producing unauthorized games because they didn't want to pay for the developer license that Nintendo was charging an arm and a leg for. But that's another story. So, this region code also exists outside of an area of the disk that is usually readable by a CD-ROM. So, if you put the disc into your computer and you tell a PS1 game, and let's say clone CD to copy the PS1 game, it's going to go ahead and it's going to create a data perfect copy of this disc for the regions it can see. But it won't boot. And the reason it won't boot is because it tries to read, the first thing it does is try to read the region code from those sectors that are outside the normal read area of a CD. Since Sony could master their stamping plates, they could put data wherever they wanted. And they decided to put the region code information outside the readable area. Again, CD burners were becoming popular, and they knew full well that this would be one of the ways that they could secure it against burners, because the burner cannot put sectors onto a disk that don't already exist. So the tracks are already burned in, and as the laser goes by, it burns pits in, but you can't go into a smaller track region than what the disk is already set up to have. And that's where they threw for example, with the Siphon Filter America one, I have SEEA into there. So that is like the first thing the console does when it reads a disk, is check that data that's outside of a normal read region and compare it against the SEEA that is in the BIOS of this console. Now, if you were in a different region, Europe, Asia, there's one other that I can never remember, but if you're in one of those other regions, I think Japan was actually separated, it's going to have a different string code in its BIOS, and even if you put a legit disc in from, let's say, Japan, it won't play on this North American console. Now, one of the things that is often missed by people who talk about PlayStation 1 security, when you read a CD-ROM, the tracks on it are kind of circular, but nothing is ever perfectly circular. So lasers in CD-ROMs, in DVD-ROMs, in writers, all kind of hover and float on a magnetic field that allows them to move in and out on the tracks and up and down to keep the disc in focus and track the data. Normally, this is just ignored by whatever is reading it because all you want is the data. Sony decided to play with this a little bit, and specifically on track 4, where in the stamping process, they put a very specific wiggle into the track. So when the console goes to read data on track 4, which should be a very specific piece of information that is provided by Sony to the person who's making it, to the authorized content provider that's producing the game, it should detect the wiggle. Now, Sony took the CD electronics and made sure that the main processor could also determine where the head is relative to the position. And it looks for, as I said, the wiggle. If it doesn't see it, it knows the disk isn't legit and it refuses to boot it. Now, most CD burners and most CD-ROMs can't even record where the wiggle that's going on, but even if you could, the CD burner can't change the track info that's on the blank. That has to be done through stamping. So they kind of put that in place too, and again, kind of a second tier effort to secure against a world where CD burners were becoming very popular. I would dare say that CD burners became more popular because of the PS1, and the PS1 became more popular because of CD burners. So, how was the security of the PlayStation 1 defeated? Well, in a couple of stages, actually. The first thing people noticed, and noted while they were working with the PS1, is that if you put in a legit disc and you turn on the console, it will spin up the legit disc, it will read the security information, and it will try to start the game. Now, usually there's a bit of a pause. And by a bit, I mean about a second. And if in that second you take the legit disc out and put a burned disc in, for many games, especially older games, this would be enough, right? It would go through and it would play the game as if it had been perfectly legit from the beginning. This became so popular that there was actually products developed like Swap Magic. Swap Magic managed to stamp their own discs. And what it would do is it would pass all of the PlayStation 1 security checks and then it would pause the CD-ROM. So you literally could take your time in taking the game out of the tray and putting your burned game in. Now, this for me defeated one of the main purposes of circumventing security on consoles. And that's that I want to protect my investment. So, with a PlayStation 1, for example, a copy of Final Fantasy VII that's in excellent shape right now is $125. I don't want to be swapping that in and out of a console and scratching it, or risk scratching it, and risk damaging it every time I put it in. So for me, one of the big reasons of bypassing the security, aside from, the whole InfoSec, let's learn about how the security works on these devices, was to be able to protect investments in expensive games. Swap Magic obviously won't do that. So the next thing to come out, and most of you have probably heard about this, would have been the first generation of mod chips. Now, what a mod chip did in this situation, and in this sense for the Sony PlayStation 1, it is an 8-bit microcontroller, usually an 8-pin. Originally it was PIC, so it was relatively easy to program for, and you could generally pick them up for a few dollars. I think they were 8 or 10 at the time. Now they're about 65 cents. And what it would do is it would wait for a signal on one of the pins, and then it would play the data stream back as if the CD-ROM had seen A, the proper region code, and B, the wiggle. So, for a long time that worked, right? And for a long time that was the way things were done. Sony kept bringing out new hardware models of this console. For example, if we take a look at the bottom of this one, right, you can see that it is, let's see what you can see. It is an SCPH 9001 console, and it was produced in November of 1999. Now, this started off with the 1001, which was a pretty easy mod. The pads that you had to attach to were fairly big, and there wasn't many of them. With the 9001, which was, I think, the last model of the PS1, there's more points that need to be soldered to, and some of them are generally like the pin of a chip or a via next to it, which, if you're not skilled at soldering, is probably a no-go for you. We will be modding this one in the next video, and I will show you exactly how I go through that process. So the next step, the next thing that happened, game manufacturers got smart, and they wanted to prevent the piracy just as much as Sony did. So they started calling for the region code at times you wouldn't expect them to. So the problem with the first generation of mod chips was they were always on. If it saw that signal come through on a data line asking for the region code information, or if a wiggle was present, it would just say, yes, and here's your region code information. There are times in a legit program's execution where calling this should fail. Spyro the Dragon was a very big game that pointed this out. So what they would do is they would call for the region code information at a time when that call should fail. And if it succeeded, they knew the system had a mod chip, and then they assumed that the game was pirated. Ironically, if it had a mod chip and you put a regular disc into the game, so you had a license for Spyro, it still wouldn't play properly because it detected the mod chip, which, in all honesty, I considered kind of not fair, because there's nothing illegal about a mod chip. If you wanted to detect piracy and stop piracy, that's one thing. And I completely 100% understand trying to stop piracy. But a fair use backup of a game should be fine, right? The original game, there's no question. Whether there's a mod chip in the console or not, a mod chip and modding your console is not illegal. You shouldn't be able to stop me from playing a game that I paid for a license for because you don't like what I did. So what happened next was the second generation of mod chips came out, and they were known as stealth mod chips. And the stealth came from the fact that they would stay on for the maximum amount of time the console should need to read the security information off of the disk, and then it would go to sleep. And this was based off of a timer that would start as soon as the chip received power. So what this did is, when you're 20 minutes into playing your game and it turns around and wants to get the region information again to authenticate, now the chip isn't there and the call fails, like it should. And the game assumes that it's a legit game, and we continue on. As I said, there was a little bit of cat and mouse, not as much as a modern console, because again, it costs Sony a lot of money, a lot of time, and a lot of effort to put out new revisions of these consoles. Whereas the newer consoles like the PS3 and the Xbox 360, they can release new firmware over the internet whenever they want. So we see a lot more iteration in the security between those. So where we are in 2020, there is a project called PSNI. PSNI is an open source Arduino-based PS1 mod chip. Okay, so what we're going to do right now, I have taken the project, the PSNI project, I've checked out the code. There was a lot of defines and a lot of bouncing around in the code based off of A, what type of Arduino are you using, and B, what kind of console do you have. I wanted to make this much clearer, so I basically took everything out that didn't apply to this console so that we can take a look at the source code as it stands for the PS1 mod chip, and we can see the security things that I talked about here and how this mod chip gets around it. Alright, so here we are at the source code for the PSNI project. As I said in the previous section, I kind of stripped it back a little bit. There's a lot of defines for using other hardware, and I wanted to be a little more clear. So we have, the first thing we do is we include the program space header. Now what this does is this gives us the ability to reference program memory and work inside of there, and as you'll see in a few minutes, they store the actual injection bit pattern for the region locks into program memory and pull it out that way later. Why they chose to do it that way, not entirely sure, but it works, so I'm not going to complain. So we have 4 basically data lines that we sit and we watch for information to happen, and then we flop the data pin from input to output a lot so that we can watch what's happening on the data bus, and then we can inject into the data bus. And I'll show you what that looks like on the scope in a couple minutes. And then we have a couple more defines that set up pins and ports for the thing itself, and one global boolean, which is PU22 mode. So there is different modes in which the mod chip has to work based off of the firmware and hardware version of the PS1 that you're working with, obviously. Next is some things that we can tailor for having issues with the mod chip. the delay between each bit that we send when we do an injection, and the delay between injections. So how long do we wait to try to re-inject if we don't think we got it the first time? Now, these can be tailored to the machine that you have. However, I have never had an issue with the consoles I've done just using the default settings that are here. So the first thing we do is we set the data pin to an input because we want to listen to what the console is doing. That will tell us when we need to actually inject. We also send the gate pin to input, the sub Q pin to input, and the squawk pin to input. This lets us just kind of snoop on the console as to what's going on. So we have our sub-channel data, both the data line and the clock line. We have our gate line, and we have our data line. So the first thing we want to do during setup is we want to wait until the system has stabilized itself. So one of the things, and I'll throw a picture up right here, of a couple of the signals that come through when the console is just idle. So it thinks that the door is open, it's not trying to load a game, it's not trying to authorize a disk, it's not trying to do any of that stuff, it's just sitting there. We use this information to determine whether or not the console's power has stabilized and whether it is ready to do things. So we also can use these two signals to determine which board we're trying to inject into. Now I'm going to throw up a capture on my oscilloscope of the signal right here, and you'll see that we are a P22 or newer board. So basically what we want to do is we want to sample this over time and be kind of a really slow, really crappy oscilloscope. So what we do is for 1 second, we just constantly read. And if the gate pin is high, then we increment the number of highs. If the gate pin is low, we increment the number of lows. Right, and then we wait 20 milliseconds. So we get about 5,000 reads. And then we look at the readouts of it. So if we have more than 100 lows, it's definitely going to be a pin mode 2, judging by this pattern. Because with PU7 or a PU20 board, gate should start low and go high, and then just remain high the entire time through. With a PU22, gate fluctuates, as you can see in the scope output that I put up. So we know that we are PU22 mode for this injection. Now, they go ahead and they disable a bunch of the extra features inside of an 18 mega 328. I don't know why. I have no reason to assume that you would need to, but they call it for power saving. So I'm not going to take it out because it does work. And then we set the output LED to low, indicating to the user that the setup for the mod chip is complete. So obviously after setup, like any Arduino program, we fall into the loop. Right, we declare a couple of variables, which are clock counters and buffers and samples, and what bit position we are at for an injection. And then we wait 1 millisecond. This, when you're dealing with a 16 megahertz microcontroller as your mod chip, it is much faster than the rest of the hardware in the PS1. So it needs to be slowed down. And this is their artificial way of slowing down the Arduino so that it can interface better with the PS1. So we're going to start to enter a critical phase of the operation of the mod chip. So we want to disable interrupts so that we don't get interrupted. And then he uses a jump area start and then go to commands. Now, you can all imagine how I feel about go to commands, but this is how we did it. I didn't write the code. It's not my code, and it works. So we reset the bit position to 0, right? And we start looping through the first 8 bits as we get it, right? And then we bit read the data coming off of it, and we wait for the clock to go low. All right, a timeout results in 12 bytes. Right, in the case the PSX sends a malformed clock pulses. right? That can happen during boot up. So we talked about the console stabilizing, and if we get malformed clock pulses, we're definitely not in a stable mode. Right, and we set the timeout clock counter ++, right? Just lets us know that we are not ready to do anything at this point, and we just keep moving through. So we wait for the clock to go high, right? And then we sample the data that's coming in on the PSX bus. And we constantly compare and bit shift and move things in. If we have an entire write, we move the buffer over to the variable that we want to deal with. We move the position over once more, and we go through and we read it again. So we basically repeat that entire process for all 12 bytes, which is your standard packet on the PSX data line. Once we have all 12 bytes processed, we can turn interrupts back on. This mod chip, the PSN, does stealth a little differently than the other mod chips that I've reviewed in the past. The other mod chips, as I mentioned, do stealth by turning themselves off after a certain number of times. This mod chip, through this massively kind of complex code, determines if it's being called for the region, where is the position of the head, and are we seeing a track wobble? Right, obviously we generally, with a burned disk, are not seeing the track wobble that we talked about. And once we go through and we get through all of that process of determining are we in the right area, right, we start with injecting data. So we want to make sure that we've waited as long as we need to wait between injections, because while we're going to send 3 or 4 or 5 or 9 injection patterns into the data stream, we don't want to do it too fast, otherwise it will be pointless, and the processor in the PlayStation will not even be able to keep up. So I have limited this down. The other one injected every region possible, right, so that it would catch the right one eventually. I'm just having it inject the SEX America, right, and if we go up to the inject SEX function up here, what we are doing is we first off have the bit patterns in various different types and various different ways of storing it, and you can see the last generation they've moved it to program memory. Alright, fair enough. There was probably more than enough memory on this chip, but maybe on others you need to be a little more frugal. Right, so we go through and we go through the bit counter, and we're making sure that we're doing less than 44 bits, which is the size of the region string. We go through and we set pin mode to output again. Right, again we flip-flop data a bit between snooping and injecting. Right, we determine when now is, right, with the micros command. Keep in mind this is micros, not millis, so it's a different return rate than millis. Right, we gate sample by bit reading it again, and then we write the data out, right, which tells it that the region is SCEA and that it saw the wobble and that everything is nice and happy. The gap in between of however long the delayed bits is until we run through that entire screen. Then we set the pin mode to output again. We didn't have to do this all this time, but this is what we do. We clear the bits, and we pull the data pin low, and we delay between the next injection before we're ready to go back and do another injection through. And this will do about 6 injections per cycle through, and as you can see, it does work. Now, again, this isn't my code. I probably would have written it a little differently, but it does work, and we get to see what is going on in the background. Then in the next video, I'm going to take a Pro Mini. I'm going to burn the PSN firmware that we are going to look at now onto the Pro Mini. I'm going to install it into my trusty PS1, and we're going to see if my backed up copy of Siphon Filter, again, before anybody accuses me of piracy, Siphon Filter 3, copy of the disc I own, and we're going to see if this PSN mod chip meaning you can spend, $3 to buy an Arduino and make yourself a mod chip for these things. Really works. So I want to thank you for joining me in the lab. If you like this video, give it a thumbs up. If you really like this video, consider subscribing. I hope you learned something today, and we will speak again soon.